Hi everyone, we're just going to go ahead and start getting some supplementary questions onto the videos for you. So this is the second section and we're starting on slide 280. Now we already did this one in one of the videos, so I'm just going to quickly go through 2, 3 and 4 for you, and we're looking for the modulus and the argument of those complex numbers. So let's start off with part 2. So we're looking for the modulus of -3 minus 3i, and you'll recall that the modulus is equal to the square root of the, if my complex number is x plus iy, the modulus of z is equal to the square root of x squared plus y squared. So this is just the square root of -3 squared plus -3 squared, so that's equal to the square root of 9 plus 9, so it's root 18, so that's 3 root 2. The argument of z is theta, such that tan theta equals y over x, so that's our general way of finding the argument. So our y here is so don't forget to draw yourself a picture before you start doing that. So our complex number -3 minus 3i is down in quadrant 3. And when we look at tan theta, it's y over x, so our y is -3 and our x is -3, so tan theta equals 1. But our complex number is in quadrant 3, so we're going around that way to get there. So theta should be equal to -3 pi on 4. Okay, so that's part 2. Part 3, it's all just the same. So the modulus of 3 plus 4i is equal to the square root of 3 squared plus 4 squared. So this is equal to the square root of 9 plus 16. So that's just 5. Again, draw yourself a picture. So the complex number is 3 plus 4i. So it's up here in quadrant 1. So we're looking for that angle there. So we've got tan theta is equal to y over x. So it's 4 on 3. And this isn't one of our nice numbers that we can use for our special triangles that we can use to find exact values. So we're just going to write this as theta equals arctan 4/3. And this is okay because we're in quadrant 1, so we can write that as arctan. Okay, so for part 4, the complex number is just -7, and this one's particularly easy. So the modulus of -7 is just equal to the square root of -7 squared plus 0 squared. So that's just the square root of 49, so that gives me 7. And again, draw a picture so you know where the complex number is. So -7 is here on the real axis. And when you try and look at tan theta, you want to put y, which is 0 over x, which is -7. So this is going to give you 0. And where is tan theta equal to 0? Well, it's where theta equals pi. If you think about what's going on in this picture. So here the argument of z is equal to pi, and you could have just read that straight off the diagram. The next gap that I'm going to fill in for you is on slide 285. We did this one on the video already, And so I'm just going to do this example for you. And what we want to do is write the complex number z as a polar form complex number. So it's r times cos theta plus I sine theta, where r is equal to mod z and theta is the argument of z. So it's just the same as the example the two examples that we've just done, but now we're just going to put them all together and write the complex number in polar form. So the modulus of z is equal to the square root of x squared, so that's minus 1 squared, plus y squared, so again that's minus 1 squared in this example, and so that's just the square root of 1 plus 1, so that's root 2. And as always, before you find the argument of z, make sure you know where the complex number is. So minus 1 minus I, so it's down here in quadrant 3. So the argument of z is theta, where tan theta is y on x, so our y is minus 1, our x is also minus 1, so that just gives me 1. So theta is minus 3 pi on 4. So now I just have to put that together. We've got z equals r, and our r is just the modulus of z, so that's root 2 cos theta, and our theta is minus 3 pi on 4 plus I sine theta, so it's sine minus 3 pi on 4. So that's z written in polar form. So the last example I've got to fill in this section is on slide 289, and this one thinks about writing the complex number in Cartesian form when it's given to you in exponential polar form. So basically what we're trying to do is undo the process that we've just been talking about. So if z is 5e to the I 3 pi on 4, it's actually pretty easy to rewrite this in Cartesian form. So the 5 sits out the front, and I'm just going to expand what this means. So remember, e to the I theta is just cos theta, so in this case it's 3 pi on 4, plus I sine theta, and we're just going to evaluate cos and sine at 3 pi on 4. So cos of 3 pi on 4 is just minus 1 on root 2, and sine of 3 pi on 4 is 1 on root 2. So this just gives you minus 5 on root 2 plus I times 5 on root 2, and it's that easy.